So we welcome Yusuke from NTT to talk about proof cryptanalysis of Chacha beating PNBs with bit puncturing.
Thank you very much for introduction. So I'm Yosuke Todo. I'd like to talk about improved cryptanalysis of Chacha beating PNB with bit puncturing. So first of all, so the focus of this workshop is a tool and automatic blah blah blah. So but in my talk, so it's a tool. It's a new tool, new theory, but not automatic tool. So but it's actually this is an open problem. So how to automate so that this a new technique. So this is my open problem. Okay, so first history of Chacha. So maybe everyone knows Chacha. So because it's a one of the most famous deployed stream cipher, I think. And the Chacha uses the ARX design. So of course, so the Chacha is well used. So cryptanalysis and understanding the security is very demanded. But unfortunately, to the best of my knowledge, almost all cryptanalysis against the Chacha is based on probabilistic neutral bits technique, and the PNB techniques was proposed at the FSE 2008. It means in past 15 years, there is no significant progress from the original PNB works. So why this is a problem? So PNB is a fully experimental black box analysis. It means, okay, we passed a key recovery map, and so the PNB analyze a round function in black box manner. We never analyze the inside. So actually, usually when we develop the key recovery algorithm, we analyze the inside of the round function, and we consider the procedures, and so we finally get a nice attack algorithm, and it's a very nice good time complexity. But unfortunately, our such in-depth analysis have failed to overcome the experimental black box analysis. So it's not convincing for me, so that such a experimental work is the best. So actually at Crypto 2020, so 5 years ago, so I also have the same problem and tackle the Chacha cryptanalysis, and I propose the advanced partitioning techniques. But unfortunately, so that this technique can improve the 6-round attack, but fail to improve the 7-round attack. So this is my rematch. Okay, so the technique is puncturing. So this is a proposed at Eurocrypt last year. So this is a novel method to approximate the key recovery map. So we first have the key recovery map as key recovery map for the linear attack. So we first analyze the key recovery map from its Walsh spectrum, and then we some non-zero coefficients of the Walsh spectrum changed to 0. So we modify the Walsh spectrum. So we say this behavior is puncturing. So of course, after punctured, this key recovery map is no longer the same as the original. So to compensate as a puncturing, we need more data. So, but finally, so we need more data, but the time complexity is dramatically reduced. So finally, we get better linear key recovery attack against S-box-based cipher. This is the Eurocrypt last year's result. So now we want to apply this idea to ARX ciphers, but very difficult because analyzing Walsh spectrum of the ARX design is very challenging. So we propose a new tool, so-called the trail enumeration puncturing, and finally, so that we can successfully replace PNB. So this is a summary of results. So the almost 30 bit or 20 bits improvement from the previous best attack. Okay, so review of the existing, what is difficult, what is the problem? Okay, so this is a Chacha, and Chacha internal state consists of the 4x4 matrix, and each cell contains 32 bits. So this is the quarter round of the Chacha, so it's a ARX, modular addition, X1 rotations. Each odd round, we apply this quarter round to each column. And even round, we apply the same quarter round for every diagonals. And finally, so the after R round, so the key stream is generated by the adding the initial state with the output R round state. So PNB is a kind of the differential linear cryptanalysis. So the idea is we first prepare two texts, CKT and CKT plus delta, and fix the delta. So differential linear distinguisher is defined by autocorrelations like this. So the input difference is the delta, and the gamma is the output linear mask. And if this autocorrelation is highly biased, we can have a good differential linear distinguisher. So key recovery is also simple. So that we first guess the key and check and compute the E2 inverse and check this linear mask. If we guess the key correctly, of course, this is the output of the distinguisher. So we observe bias. If the guess is wrong, it's a random. Of course, it's a hypothesis. But what is the problem? So of course, this is the same. This structure is the same as the S-box-based ciphers, but in the case of the ARX, only a few rounds. In the case of the Cha-Cha, so the only 1 round or 2 rounds. After 2 rounds or a few rounds, almost full bits of key is involved. So it means, okay, I want to compute this value. We need to guess almost all full key bit K. And then, of course, so the time complexity to evaluate this equation is extremely high. To counter this problem, Omerson et al. FSC 2008 proposed the probabilistic neutral bits technique. This technique is based on the knowledge. So yes, so actually, this is if E2 is ARX design, indeed, almost all full key bits of the K is involved. But some key bits are not impacted to the parity. So they approximate the key recovery function E2 inverse to the some approximations, so such that the involved key bit is significantly reduced from the original. So like this, so the G is the ZZ prime is the output of the key stream, but K is just a truncation. But how to obtain such G? The method is very simple. So we divide K into 2 parts. One part is guessed bit part, so significant key bits. And another part is a probabilistic neutral bits. Usually, so that we set the PNB to the fixed constant value, and usually it's 0. So it means this is the original key recovery map. So that we simply set some, we guess this red part only, and other part we simply use all 0. So to identify the probabilistic neutral bits, the method is very also simple. So that we first check this key recovery map, and then we just flip 1 bit and get the correlations. And if this correlation is higher than threshold, we identify bit is as a candidate of the PNBs and try all bits. And finally, so that we get this list, this case, and finally get the correlations between these 2 functions experimentally. However, so that this analysis is fully black box analysis. So of course, this algorithm doesn't depend on the inside of the E2. So we never analyze the inside of E2 carefully, and there is no plausible evidence. Yeah, so we set 0 for PNB. So original paper say, so if we use all 0 here, it's highly correlated. So we use it, but no reason. Actually, very recently, I read that one paper. Oh, instead of all 0, 1, 0, 0, 1, 0 star is much adequate. But no reason. Again, so it's very problematic for me to improve the attack. And also we need to remember PNB a key in original. There is no reason why key is 0. So actually we have the same problem in the statistics. For example, okay, this is my experimental result. So orange is a long case, so it's a normal distribution. Yes, almost, yeah, looks like a normal distribution. And blue case is a probabilistic neutral bits case. It's, of course, not normal distribution. And there are a significant gap between average and median. Of course, so in the PNB, we use all 0 here. In case the used key satisfies all 0 here, the correlation is 1. But of course, if this is another value, the correlation is worse. And the distribution is like such biased one. So original paper suggests we should use the median instead of the average. And success probability is almost 50%. Okay, so now new theory and new tool. First, mathematical background. So we first define the key recovery function as a Boolean function. So key f is a Boolean function from f2 to the n to f2. And Wolf spectrum is defined like this. So the f, and we simply say f hat. And the correlation is defined like this. So the f inner product between f and g. So FT24, so the last Eurocrypt paper, so that I propose the approximations and penalty. So let f is a Boolean original key recovery function. Now we approximate f into should Boolean function g. It's very important. So should Boolean function, original function is a Boolean function. It means the output is 0 or 1, so or -1 or 1. But here, so after approximations, the output of the should Boolean function is real valued. It takes real values. So for example, 0.25 or blah blah blah. And corollary 3 say if we use g instead of f to take the same advantage, the sample size is increased by a factor of 1 over rho square, and rho is this formula. And also, as the same paper, so I introduced the Wolf spectrum puncturing, the new technique. So f is a balanced Boolean function, and f hat is a Wolf spectrum. So we prepare the subset of the p, and if the coefficient of u is belong to the p, we puncture this Wolf spectrum coefficient. Otherwise, we use the original. In that case, the puncturing correlation is defined like this. It's very simple. But of course, it's just a mathematical representation. Probably everyone can't understand the effect only by this explanation. So I want to introduce very easy example. And also, I hope everyone understands this usefulness. Okay, so now we want to evaluate this bit as a key recovery function under linear cryptanalysis. So plaintext is x is of course known. If we guess 60-bit k and 4-bit k here, in total 20-bit key, of course we can compute this bit with perfect accuracy, of course. Now, so that we define f is -1 to this inner product. Then f is like this, so the 1 minus 1 blah blah blah. And also f hat is the corresponding Wolf spectrum. So now what we do? So we first puncture the all coefficient whose MSB is 1. So now, the punctured whole spectrum is G hat. And then we reconstruct the corresponding Schur Boolean function is like this. In that case, puncturing correlation, rho square is 2 to the minus 1. So it means we need double data. But one nice thing we have, so here, MSB is no longer related. So we can exclude this bit from the key recovery map. And also this bit comes from the fourth S box here, but it's also excluded. So it means we need double data, but we can reduce 5-bit key guess. So it's very nice trade-off. And also we have more tricky case. For example, we just puncture one coefficient for the F. In that case, so the corresponding Schur Boolean function is indeed real value. And then, so the rho square is only 1 minus 2 to the minus 4. So the penalty of the data complexity is very, very limited. But the dimension of the key recovery map decreases to 12 from 16. In that case, so if we use first-order Hadamard transform techniques, and also we use the linearity, then we can reduce the time complexity significantly. But it's, of course, a tricky case of the FWHT technique. OK, so now we want to apply this idea to ARX. But it's a problem. What is the problem? Now, so that this is a quote around, we want to evaluate A double prime 12 from Z with key guessing. So original key recovery function is this. So the minus 1 to the A double prime 12 is, yeah, so it involves 83-bit output and 57-bit key in total. So if we want to evaluate this bit with perfect accuracy, we must guess 57-bit key. And also we need to use 83-bit output. It's, of course, very time consuming. OK, so now we want to reduce, we want to approximate this key recovery function to the much simpler one. But now we want to use the same idea to the Eurocrypt last year papers, but unfortunately it doesn't work. Why? So we first apply the puncturing to the first modular addition, so red circle. But even if we puncture some whole spectrums here, so after that, so that we have modular additions again, and also the modular additions again. So unfortunately, we can't exclude any key bits from the key recovery map. But why we have nice useful observation, but it's very simple. So each Walsh coefficient is correlation of the linear approximation. Of course, it's maybe everyone know, I hope. And also, correlation of the linear approximation is the sum of the signed correlation of all linear traits in the approximation's linear hull. So in that case, so this ARX is highly biased. So we just enumerate linear trails with nice high correlations. It's after that, so that it's very nice, nice, good precisions for the Walsh spectrum. So this is the example. Okay, now we want to compute these 12 bits, and the corresponding linear mask is here. So only one coefficient. Okay, so first we apply the first module. We first analyze the first modular additions. But here we only focus on the 2 bits of the C prime. And if the linear mask of the C prime is active in the 10-bit to 0-bit, we puncture such coefficients. After that, we got 26 coefficients in this part. And next, we analyze the next modular additions and extend the trail. if some trail goes to the same if some different linear mask transit to the same linear mask, of course, in that case, due to the linear Hall effect, output linear mask is the sum of the correlations of the two linear trails. And finally, we got only 8 coefficients, and each coefficient takes these correlations. And finally, we analyze the modular additions here. Then we get 768 coefficients. And the dimension is 2 to the 10. And rho square is 2 to the minus 6.17. Okay. And finally, we apply the inverse first Walsh-Hadamard transform. This cost is the 10 times 2 to the 10. And then we have a Schur Boolean function. Okay. So if we use Schur Boolean function instead of the original Boolean function, we need to use additional 2 to the 6.17 data. 2 to the 6.17 times data. So original data complexity is the n. We need 2 to the 6.17 n data. But finally, we have the same attack. If we use it, only 4-bit key guess is enough. Okay. Originally, we must guess 57-bit key. But here, only 4-bit key guess. But we need more additional 2 to the 6.17 times data. So what is the difference from PNB? So PNB is experimental analysis, but puncturing is the theoretical analysis. It means even if the correlation is extremely low, for example, 2 to the minus 32 or 40 or something, in that case, we never observe such a low correlations experimentally. But puncturing is a theoretical analysis, we can find it. And also, very significant difference is PNB, each output of the approximation is bool. It's a 0 or 1. But puncturing, it's a real value. So it's essentially different. And PNB, so the correlation depends on the key heavily, but the puncturing correlation is the key average. Okay, so now we want to apply this idea to CHA-6. So first we use the 4.5 round differential linear distinguishers. And we want to analyze the key recovery map. Only 3 rounds key recovery map. But now, after evaluating the key, after analyzing the key recovery function, we found only 2 bits. This bit and this bit involves the more than 1 modular additions. Other bit, for example, here, only 1 modular addition, so we can immediately compute by guessing the sum key bit. So these 2 bits are complicated. So first, we want to analyze this bit, and this red line is this diffusions to compute this bit. And finally, so that we use the trade enumeration technique. And yeah, so I enumerated this coefficient, and then puncturing correlation is this. And also this part is the different positions, and also enumerate this coefficient, and the puncturing correlation is like this. Okay, so finally we get the parameters. So the puncturing correlation is the minus 3.54. And there are 18 functions consisting of only 1 modular additions. And for this bit, so we only get 2-bit key. And the puncturing correlation is to the minus 7.47, and in total, 2 to the minus 11.01. So it means original key recovery function, instead of the original key recovery function, we use the puncturing function. Then we need to more 2 to the 11.01 times data. But in our case, it's a differential linear DAG. So we have two paths in the differential linear. So we need 2 to the 11.01 times 2 data complexity. And also, we can further improve this attack by using the distribution table technique. So the original Matsu's paper. So originally, the time complexity is n times 2 to the k. But by using the distribution table, so that we can reduce this time complexity to n plus 2 to the b plus k. And if n is more than 2 to the b, using the distribution table is much useful. So by using this idea, so we can further reduce the time complexity, and the time complexity that is 61.40. Okay, so this is the experimental result. Of course, so the including the differential linear distinguisher, so the correlation is too low. So this experiment only analyzes the backward correlation. So to understand the difference between the PNB and the puncturing, I implement the both case. This is the case of the PNB, and this is the case of the puncturing, with the same data with same key bit guess and with same sample size. Clearly, we can't distinguish anything in PNB. So almost the same distributions in long and light. But in the same with the puncturing, unfortunately, variance is a bit wide than theory, but we can distinguish. So now we use more data. Sorry, no, data sample size is the same, but we guess more key bit. So this case only 5-bit guess, but we guess 30-bit key guess. In that case, okay, P and B is a so probably we can distinguish. Here is overlapped, but maybe distinguished. And so that this case clearly we can distinguish two words. So P and B's. So we can conclude that puncturing is better than P and B's. Okay, so the 7-round attack, actually we use the same analysis, but key recovery function is now 4 rounds, not 3 rounds. Much complicated. But yeah, so most deep part is here. So we analyze this key recovery functions, and also by combining. Yes, so this is a summary of the puncturing correlations. So we need many data increase to compensate the puncturing, but the guessed key size is very limited than PNB techniques. Okay, so this is a summary. So 7 rounds, so the previous best attack is to the almost 190, but now to the 150. So 40-bit key, 40-bit improvement. And also 7.5 rounds. Original attack used the 255.2 time complexity, but success probability maybe 50% because it's PNB. So it's a bit controversial situations. But now so the new attack is to the 250 with success probability is almost 1. Okay, so summary of my talk. So I propose a new tool to analyze the cha-cha. So I hope no more PNBs. Please use puncturing instead of PNB, I hope. So free theoretical analysis is now possible. So we don't need to rely on experimental work like PNB. And significant improvement of cha-cha. So, and in this case, so each unit of the time complexity is 1 table lookup. And next step coming soon, so that we are now apply this idea to salsa. But now so that we have a bit so complicated situation, but now we come up with new techniques to improve the efficiency, and so, but it's just ongoing. So I hope we can write paper soon. But of course, so that in the perspective of this workshop. So I want to say open problem about inspires the motivation of this workshop. So maybe, probably, everyone loves differentials and linear. Do you agree? Everyone loves Bihams and Matsui-san? I'm not sure. So, okay. Linear key recovery, probably very, very complicated and more mathematics, I guess, than differential key recovery. So, for example, sometimes by using the Walsh spectrum, we can improve the attack. And first Walsh-Hadamard transform, it's a bit complicated to understand the background. And also now new technique puncturing, it's very situations complicated. And also we can sometimes exploit the linearity of the Walsh spectrum. It's also Antonio's Asia Crypt 2022 papers. So it's very, very difficult. But maybe as far as I heard the many talks in this workshop, yeah, everyone focus on automation, automatic key recovery is very important. But I think everyone did differential, rectangle, boomerang. Key recovery is everything is differential in this case. No one tackles the key recovery for linear attack. Please do it. It's very difficult question. So actually, in the Eurocrypt last year, so I analyzed the puncturing to the SBox-based cipher. So I want to improve the attack. I improved the serpent, gift, press, serpent, gift, and so on. So, but very heuristic. This is my heuristic. So it's my pencil and pen attack. So the probably puncturing here is the best. I did it not so okay. I tried to next here. Oh, okay, it's very nice. Something like this. It's a very heuristic, no automatic tool. So tool is demanded. So please read puncturing papers and please come up with a nice tool. Thank you very much.
Thank you, Zuka. Is there any question from the audience? Yes.
Very nice. So when we did this paper in 2008 about the PNBs, we were inspired by hash cryptanalysis. So the neutral bit technique to speed up collision search. My question is now, can you turn your new result around and map it back to the hash setting, to the keyless setting? I know it's a bit of a stretch, but is that completely out of the question? Yes. Well, the inspiration came from a subroutine in a collision search where you speed up the process to find messages that conform your differential trail for a number of rounds. So basically have more trails, more message pairs for the same computation than without those neutral bits.
Differential attack includes the differential linear attack. So the differential part is got the differential attack, but the key recovery part is the linear attack because it's a differential linear. So this technique improves the linear key recovery part. So far, for me, it's not trivial to apply this idea to analysis of the hash function as a linear application to the linear cryptanalysis to hash function is not trivial.
All right, yeah, thanks. Let's see.
There was also in the past.
So, yeah, I felt like this this wall spectrum puncturing techniques seems a lot like just multiple linear cryptanalysis, where you properly like track the sign of your approximations. Like, did you look into like how this compares to multiple linear cryptanalysis? Maybe you can also get some ideas from there on how to like automate your approximations.
So if we don't get the key, of course, the sign information is we cannot recover the sign perfectly. But in this case, so we get the key and we can compute the sign information to everything, and we can combine all information to the whole spectrum. So it's possible because it's key recovery. But the multiple and multidimensional linear distinguisher part usually is not get the key, and we cannot combine. So it's a bit different. But yes, conceptually it's the key.
Thanks.
In 2015, you proposed recover integral using Walsh-Hadamard transformation. So my question is it possible to transfer this for So for integral attack also, you can use Hadamard transformation for key recovery, right? So is it possible to transfer this thing to integral attack? So that's my question. Yes. Exact value. Right. Okay.
Okay, I think we can thank you, Yuzuki, again.